Hi, my name is Jared Yu. This is the Mechanisms of Action Kaggle competition, and so I'm going to be using the data mine techniques learned in class and applying them to this data set. So what we're going to go over is the context. So what is Kaggle? What is this competition? Talk about exploratory data analysis, looking at the data, how it's going to be modeled, using traditional techniques, adding feature engineering, and then progressing towards neural networks. And we're going to look at the results of these methods, looking at comparisons to the other competitors, and then we're going to have some concluding remarks. So, what is Kaggle? Kaggle's I guess most of you already know, but it's a data science community. So there's different people, like experts from around the world, and they contribute together and they share their knowledge. And there's these competitions hosted by these big companies, and like oftentimes there's big, huge cash prizes, and you gain rank. Um, So there's always a competition metric, and that's like one of the critiques about Kaggle because on the leaderboard with all the competitors, there's a single score that they gauge you on, and there's a public and a private leaderboard. So the public leaderboard is when everyone can see everyone's current results, and the private leaderboard is the test data that hasn't been shown. And so looking at this competition, what do we have? We have mechanisms of actions, which is a hosted by the Laboratory of Innovation Science at Harvard, and it's basically a really complicated data set. It's hard to understand in the variables, and this is part of the reason why I chose a project because it's sort of interesting in that regard. It's similar to another competition that was hosted before by a Santander Bank where all the data is anonymized, so you don't really know what any of the variables mean. And that's pretty much what's going on here. Furthermore, it's not a typical binary multi-class classification problem. It's a multi-label classification problem. So an example of this is computer vision, where you have like an image and to detect whether there's a cat, a dog, a person, or all of the above within the image. And so the evaluation metric, the competition metric for this one is the log loss, which you guys should be familiar with. And so looking towards EDA, right? So we have 206 classes, so it's pretty large. And if you look at the top right, you see that around 40% have no label, 50% have one label, and around 10% have two or more. And looking to the top left, we could see actually many of the classes are only have around like 40 subjects within them. And some of them are really dense, like some have 800 and some have really few, like just one or less than 10, right? And at the bottom, you can see the sort of distribution of the sizes of the class. You can see on the left side that most of them have under 75 subjects in them, and so there's this really skewed distribution, right? And so that's going to be hard to model. Looking at the attributes, there's actually only three categorical variables, which you can see at the bottom: the sample treatment, treatment dose, and treatment duration. And then there's 772 uh, gene expression numeric variables and 100 cell viability numeric variables. And looking at the top right and top left, we could see examples of those from the data set. And they seem to have been normalized, and they're just these hard to understand variables. There's not much meaning for a layperson, especially. And so that's what's going to make this competition difficult. So in the modeling process, what we want to do is we want to basically iterate through multiple models as fast as we can and as efficient as a manner as possible so we could check out what sort of features and model architectures are best for this problem. And so some important parts of that are using things like Python libraries like scikit-learn to use these pre-made packages that have all the models done for us efficiently. And then also Visual Studio Code, which helps us to have an IDE that sort of allows for this sort of running through multiple scripts and doing it really quickly. And so what I had to do at first, I had to like basically do a quick one verse rest methodology, and then later I had to try some multiple models like logistic regression, KNN, and do this sort of hyperparameter search through all these different parameter spaces. Later on, I would be able to move on towards something like neural networks. So in this stage is feature engineering, and feature engineering is basically where we use our current data set and expand on the number of attributes by making up these new variables that before didn't exist. And so there's some ways to do that. So the good way, quote unquote, is to use these independent features, right? So for example, you have a new test subject and you want to add some features to it. You don't use any information from the training or test data, and we never mix those two because that leads to data leakage, which is a problem because if our model has data leakage issues, then there's problems with statistical dependence, and then therefore it fails to generalize properly to these real unseen subjects. And so some examples of ones that are completely independent are like row statistics, right? If we calculate the mean, median, and mode for a single subject and append those as new features, that's fine. And also, like with categorical variables, we have like three categorical variables, and we want to combine those into a single level for like as like a fourth from our three original ones. That's fine. But then there's some issues that we want to do something like dependent features, right? So example of a dependent feature is like if you want to normalize a column, right? You need to take the sample mean and the sample standard deviation. You combine the like a training and a test data set to recalculate those sample means and standard deviations, then the resulting normalization process is biased, right? So a way to work around that like would be for like in PCA is rather than calculate a new PCA for all those combined, we could just do it for a single subject, right? So we have a single test subject and we recalculate PCA, and we do this for each of all test subjects. Then we get these new features related to the principal components appended to the test subjects that are quote unquote statistically independent, but not exactly. So neural networks are really what have been the edge in this competition. All top competitors seem to be using it. And especially if you think about the case why it's simpler is if you use something like random forest, right? If we have 200 classes and we have to fit 200 different models for each of the classes, and neural networks save us from having to do any of that, right? So they have better performance, it's simpler, but there's also issues, right? It's slow to tune because there's so many hyperparameters, and coding them isn't necessarily simple, right? And they're complex also. So we use things like PyTorch and PyTorch Lightning, Optuna, which are these packages that allow us to implement neural networks in a way that makes it quicker, efficient, and more accurate. And Optuna is a good example of this hyperparameter search that's not simple grid search. We're using this sort of complex tree-based hyperparameter search space, and it allows us to do what we want in a more efficient manner, like we're referring to like this pipeline that's easy to work with and easy to iterate through. And then so let's look next at the results, right? So on the top, we could see like the baseline model. You can see how simple it is. It's just a single logistic regression model testing uh, like 6 learning rates to see which would perform best in the one versus rest setting, right? And that's just a baseline model. We get that performance. And then we look next to the mixture of models testing a mixture of hyperparameters. And you can see on the bottom table, it's kind of surprising that logistic regression outperforms all of them. That's in the yellow column. In the green column, you see mostly random forest and one XGB, and those are the cases when the cross validation scores are really similar, right? And so the most likely reason why logistic regression outdid every other one is because you could train like a large range of the learning rate pretty quickly, but for the other ones, they're really computationally expensive. It takes a lot of time, and so I had to limit the hyperparameter search for many of them. And so that's probably why logistic regression ended up getting chosen so much. And then so we could also look at the results of the feature engineering. So what I did here is in order to add a feature, I would do one at a time. I didn't do some stepwise regression sort of thing where you check all different combinations of the next new potential model. I would just add one at a time because one, this is simpler and I don't have as many computational resources to do something more uh, complex, right? And so what you see here is I looked at the baseline model with like the local cross validation scores, and now calculate a new one based on like FE1, which is the first set of features that I wanted to add, and now subtract them. And so you see in green, when it's green, that means there was no improvement. But for FE1 minus no FE,
there actually was largely an improvement. And in FE2 minus FE1, which is the second set of features, uh, compared to the first set of feature engineers, there is only one case where there was no improvement. But in FE3 and FE2, which is like the PCA features and like every other feature before, there was mostly not an improvement, but there was a key improvement in the third class, the proteasome inhibitor, right? And so that gave me enough reason to keep it because the the the, the performance when it went down was actually not by much. For like the other ones, you look at the green, they're actually really small. So I actually ended up keeping the PCA feature. And right, so now we go look at the neural networks, and what do we have? We have the model for the Model 1, Model 6, and Model 7. So Model 1 is the baseline model. We can see the CV score, the local cross-validation, the public leaderboard score. And so Model 6 is the neural network trained on the raw data with no feature engineering. And Model 7 is the same neural network retuned, including feature engineering. And so there's a pretty big issue here, right? Because the CV score is much better than the leaderboard score, so that means we're overfitting the training data, and it's not generalizing very well. Another issue is the Model 7 actually does worse. So even though the feature engineering helped the the traditional non-neural network models, the the neural network when it uses feature engineering actually had worse performance. So I wasn't able to figure out why. I was thinking maybe it's regularization issues, even though I did have a dropout term. Maybe my neural network architecture wasn't complex enough, or maybe because I wasn't training the epochs long enough during the training for the neural networks. But despite what I wanted to try, I was limited by a few factors like time and computational resources. So here we are the results on the leaderboard. On the top left, we can see like the models that do not use neural networks, and there's a slow iterative improvement within the development stage, and we can see the models getting better and better, but there's no great improvement in comparison to all the other models given by the competitors on the public leaderboard. And so looking into the top right, we have the neural networks that have been made. Right, so there's the one of the raw data and one of the features. And the raw data one actually managed to break into the top 67%, which is a pretty decent jump from where we were before, right? Like top 95, which is pretty poor. When we look at the bottom, we can see the comparison on the y-axis. The neural network is actually not too far away from the top models, right? They have like 0.0195 versus 0.0180. And I'm sure with enough time and resources spent into it, it could have gotten better, but it's not certain. So what did we learn? In conclusion, there's a great need to keep continually practicing on the ML engineering side of things because this took up the most time in the project, and being able to do this efficiently and just learning from experience is what can make future projects better. And also something is the neural networks. It became apparent that neural networks were the key to doing well in the leaderboards, and so having more knowledge and ability to implement more complex neural networks would have made a great difference. And lastly is like EDA and feature engineering, right? Because with EDA and feature engineering, you really get to make your model unique and special and different from others. And in a competition setting, when there's so many other competitors with similar neural networks, the only difference that you can really see in the end is not the model itself, but the features that you find within the data set that allow your model to surpass others. Thank you for your time.